Okay, thank you very much. Thanks for inviting me to come here and give a talk. It's great to be here. So I'm going to talk about memory-centric computing, essentially how to enable fundamentally efficient computers and also fundamentally high-performance computers, in my opinion. Okay. Today, I think you've seen a lot of talks where all of the talks point to the fact that computing is bottlenecked by data, and we have a huge problem with data. Data is really key for many workloads, including machine learning, AI, genomics. All of these workloads are data intensive. They require rapid and efficient processing of data, and data is increasing. Basically, we can generate more data than we can process in many, many domains. This is not going to end anytime soon. And we need to perform more sophisticated analyses on more data, especially if you want to really achieve some of the goals of higher intelligence, etc. And clearly, people have shown pictures like this. I'm not going to harp on this, but compute and memory requirements of machine learning models is increasing. That's true for other domains also, genomics, for example, which actually takes advantage of a lot of machine learning advancements, also has a huge data increase that's happening. So there's a lot more data to analyze. So the major problem is today's computers are not designed to handle this well. Essentially, data access is a major performance energy bottleneck. I'm going to give you some numbers to show that. I think a lot of you are familiar with this already. And our current design principles cause great energy waste. Basically, we're moving data all around between the processor and the data storage units, memory. They also cause a lot of performance loss, especially our access patterns are not nice, let's say. And we try to overcome this performance loss as much as possible by adding software and hardware techniques that complicate our systems. For example, in the hardware, we add many, many levels of hierarchies for caching, memory, prefetching, automotive execution, multi-threading. And in software, we also complicate our software to really avoid the data access as much as possible. And in many cases, we try to avoid it, but most of the time, we don't completely avoid it. As a result, our performance is also suboptimal. But what is hidden over here is the complexity. Basically, our systems are very complex because we're really trying hard to get performance despite this data access. And when these techniques don't work, we waste even more energy, essentially. So we're in this vicious cycle, in my opinion, where we keep wasting energy because we're very processor-centric in the design of our systems. All data has to go through the processor to be processed. And when I say processor, that's also an accelerator, that's also a GPU, that's also an FPGA, whatever your favorite computing unit is, that's the processor for me. And this is my cartoonish picture of that processor, let's say. If you look at that processor, most of the hardware real estate is dedicated to storing and moving data. Very small fraction in general, even in very compute-intensive systems like GPUs, for example, very small fraction of the hardware is really dedicated to things that process data, cores, as well as accelerators. So if you show this picture to maybe 10-year-old kid and say, I'm dedicating almost all of my resources to storing and moving data, I should not have any problem with it. And they will say, probably you should not have any problem with it. Unfortunately, we're still having problems with memory, and that's the major problem that we have today, in my opinion. So let me give you some data. This is Google's data, actually, not my data. This is, according to them, in 2015, all of their data center workloads. And this basically shows that in a state-of-the-art CPU system, most of the time, the processor is waiting for data, even though it's designed with all of these techniques that I mentioned. On the energy side, moving data consumes a lot of energy. This is, again, some old numbers, but the key takeaways remain. A complicated arithmetic operation in this particular picture is about 20 picojoules, according to Bill Daly's presentation. And a DRAM read or write is about 16 nanojoules. That's 800x difference. Maybe 800x is too much. If you optimize things, you get closer to 100x. Going below 100x is difficult today. And that was a complicated arithmetic operation. If you have a simpler arithmetic operation, like a 32-bit integer add, then the disparity increases. And this is just DRAM. Today, actually, we want to have even less complicated arithmetic operations, 4 bits, 2 bits, 1 bit, if it's possible. We want binarized ways of doing things. We want to minimize the multiplication, as we have seen earlier. And those are actually really great efforts, in my opinion. We want to simplify the operations. And as you simplify computation, yes, you reduce the data, but you also increase the disparity between the memory access and computation. And we're not even talking about storage yet. If you actually think about SSDs, moving data from SSDs or sensors, add another 10x to that number. Okay, so the numbers kind of go crazy a little bit. So the question to ask is, does it really make sense to move the data to a processor, move every single piece of data to a processor to process it? Should we have alternatives? So we tried to quantify the cost of this data movement with various studies. very quickly, I'll go over this. This is a study that we did a number of years ago with Google. And on average, on mobile systems, including the TensorFlow inference system at the time, we found out that more than 60% of the energy, total system energy, is spent on data moment. This becomes worse as in accelerators, because accelerators optimize computation, but they optimize data moment a little bit less than they optimize computation. And also, if you actually are using large machine learning models, they also have a memory problem. In this work, we showed that more than 90% of the total system energy is spent on memory in edge TPUs, for example. This just to give you an idea, we characterize, I'll talk about this work very briefly later on also. But if you look at this, these are at the time the largest edge neural networks used at Google. And we found out that most of the energy is spent on DRAM and off-chip interconnect. And if you move the computation to the memory side, you reduce that significantly. Okay. So basically, the fundamental problem we have in our system today is processing of data is performed far away from the data. And I think we need a paradigm shift to enable computation capability essentially wherever data resides. And data resides in a lot of places in our system, and we want to enable that computation capability everywhere. This will hopefully minimize data movement. I call it compute where it makes sense, where data resides. And we would like computing architectures to become more data-centric. Easier said than done. But this is just one example system, and you can see that we're restricting ourselves in our current system to this chiplet-based architecture, and only a very small fraction of this chiplet is actually capable of doing computation. Most of this is SRAM, actually, and buffers. And you can see the darkness on everything else. You cannot do any computation where data really resides or where data is taken in. Okay, so in the rest of this talk, I'm going to treat memory as an accelerator. Basically, we're going to push computation capability to the memory side. And today, we actually have heterogeneous accelerators. We're very good at designing many compute-centric accelerators, except they all have the same bottleneck. Why don't we design accelerators on this side of the memory bus? That's the idea. If taken to like a longer-term extreme, I think maybe accelerators are actually less too CPU-centric or too something-centric term. Maybe we want distributed agents that can collectively do some sort of computation by distributing that computation to equal agents all over the place. I'm not going to talk about that, but I think this is something that we would like to go into in the even longer term. But even with accelerators, we're going to have a lot of problems, as we will see, as you have seen earlier also, or memory-centric accelerators. And there are many questions over here. We would like to be able to query the memory, ask the question, can you accelerate this function, this instruction, or this application for me? Memory will say yes, and here are the results. That sounds good, but how do you design that compute-capable memory? What are the hardware structures? What are the interfaces to access that? How do you design the communication units and the processors after that? How do you actually design the software, compilers, and languages to take advantage of that without making people go crazy about programming them? How do you actually fit the algorithms to the underlying hardware? And how do you morph the hardware to actually design better algorithms? And I think this is really important in the machine learning domain today, because the existing hardware limits what kind of algorithms you can have. And existing algorithms may not, existing really good algorithms may not be developed because the hardware doesn't fit them well today. There's also some theoretical foundations that I'm not going to go through here, but there are clearly a lot of questions over here that I'm not going to answer all of them, but I'm going to give you a glimpse. But I should also say that we should be careful, meaning a lot of people have thought about this before. These are some of the earliest papers on processing in memory in the 1960s. I like using processing in memory, so these folks called it logic in memory, which is similar to processing in memory. These are beautiful papers. They propose near memory processing, which is easier to handle, as we will discuss. There's another paper over here. So what is different today? In my opinion, today we have nowhere to escape. Meaning, as I mentioned, we have a huge demand from application systems. I've already said all of these, except one thing I did not say, which is performance, energy, sustainability. We're at a point today, we want performance, energy efficiency, and sustainability all at the same time. And if you want to have all of it at the same time, we really need to think about minimizing data movements. So this is the higher level perspective. At the lower level, we're having a lot of issues with the memory technology as well. Our memory technologies, even though they've served us really well over many decades, they're having a lot of trouble today. For example, we're having issues with the RowHammer. I'm going to very briefly mention that, but we're having a lot of other issues also with bit flips, etc. And these technology scaling issues, as memory becomes smaller, are demanding some computation capability to actually keep the memory sane, let's say, or reliable. So for example, DRAM manufacturers today are adding computation capability inside the DRAM chips so that you can ensure the robust operation of DRAM chips. And emerging technologies also have similar issues if you want to enable emerging technologies. And they can also enable new functions in memory. So basically, today we're kind of squeezed in the middle, and we have nowhere to escape. But perhaps we need to take the leap to enable that processing in memory. So very quickly, RowHammer, there will be sessions on this. That's why I want to talk about that very briefly. These are not the only scaling issues, but these are some of the one of the like main scaling issues that has enabled that has caused the industry to add computation in the DRAM chips. Basically, if you access one row many times, you induce bit flips in nearby rows. And this issue becomes much worse in newer technologies with smaller cells. You can see that the number of accesses you need to make to a row has reduced by more than 100x in 10 years or so to induce a bit flip. To also solve this problem, people have been adding things. I'm not going to talk about that, but essentially the key is having intelligent controllers that are capable of computation. If you're interested in solutions, there are 2 sessions at HPCA that talk about some solutions, but I'll leave the suspense here today. Okay, so let's talk about processing in memory. So I use processing in memory as a general term. There are, in my opinion, 2 types of processing in memory. One is processing near memory, the other is processing using memory. Processing near memory is what we do today. You have logic, you have memory. Logic, that's called processing. You design them completely separately, and you put them at some distance. Today, we're far away. But you can imagine taking the logic closer and closer and closer and integrating inside the memory chip, integrating very near the memory cells, each bank, each subarray, under the logic layer, for example, in 3D stacking technologies. But logic and memory are separate. This is easier to do. And this is already happening, I think, in startups, and I will show you pictures over here. But still, it has some adoption issues that I will discuss. The second part is processing using memory. You have logic and memory. You don't have logic. Forget about logic. I have just memory. Some memory technology. I'm going to take advantage of the fundamental operational properties of this memory technology to do computation. Usually, these are analog operational properties, and I'm going to talk about that as well. This is a fundamentally different way of doing things because it's very different from today. I believe this is fundamentally much more efficient, but initially it may not be easily programmable or adaptable. But in the end, if you want to minimize the data movement, we would like to do both and also cater to a lot of applications and a lot of different types of operations. So we're actually combining both in our research. Maybe I'll get to it, but in the end, I'm going to talk about these 2 directions. Okay, so I think processing near memory can be done in different places, near SRAM, near DRAM, inside the DRAM banks, inside the logic layer. I'm going to talk about some of these very quickly. Processing using memory is really in the cells and the word lines and the bit lines in the circuit. Okay, so processing near memory is easier to adopt. That's why it's happening in industry and it's easier to do. So these are some example chips that are built, commercialized by Optimum, for example. They have a more general purpose DRAM chip where you have a SIMD, where you have a fine-grained multi-threaded processor next to each bank. There are also accelerators designed by Samsung, SK Hynix, more Samsung and Alibaba to actually do machine learning acceleration or recommendation inference acceleration. I will not talk about these industrial prototypes. I'd be happy to talk about them. We've done studies a lot with Optimum, for example. But the good news is there's action, and there are many experimental chips and startups that are also doing a lot of interesting things like in near SRAM computing. Another good news, I think today we have interfaces that can enable offloading of computation to somewhere other than the processor. CXL is one example of these interfaces. Having these flexible interfaces enables us to break the barrier of the CPU. If you have coherence in these interfaces, of course, even better. Again, I will not talk about these at this point. Now, let me give you 2 examples of the benefits you could get if you actually take advantage of some technology like 3D stacking. I'll talk about this one very quickly because it's a little bit older work. I'll talk about the machine learning acceleration we did also a little bit longer. So basically, going forward, we will have technologies where logic layer is going to be high quality, and we will have this logic layer underneath memory layer. So this logic layer can house many processors that are connected to the memory layers at high bandwidth, low latency, and low energy. Over time, this logic layer will become better and better due to manufacturing and packaging technology improvements. So this is a work that we've done about 10 years ago, taking advantage of a reasonably good logic layer. And the idea is to accelerate a difficult application like graph processing, which is really bound by random accesses in general. And I'll give you a very quick overview of the system. Essentially, you start with this cube or 3D stack memory plus logic. Inside the logic layer, we add an array of cores. These are in order, very simple cores because you need to satisfy the area and thermal constraints of the logic layer. And each in order core controls the memory on top of it and owns it. And the idea is, if you want to update a data, a graph node, you send a message to the in-order core that owns that data. You partition your graph across these nodes, and you program this using remote function calls, remote procedure calls, just like you do distributed systems, and you do the updates using remote function calls. So you don't move the data to the processor that's going to update it, you move the function to the data, and the data remains intact and where it's partitioned. And of course, to be able to scale the system, this memory is not enough. Today is not enough also, as people are seeing with GPUs. Today, actually, GPUs are made bigger and bigger so that you can get very high memory capacities, right? Similarly, we have a distributed system or an interconnected system of these 3D cubes where you can partition the graph. This could be done for machine learning also, but this is graph in our case. Okay, so that's the idea. Let me give you quick performance numbers. Clearly, this is a very large system design. There's a lot of detail that I'm omitting over here. But the takeaway over here is that this system doesn't look like any of the systems that we have today or that we had at the time. Because compute and memory are coupled, and then you have a distributed system of that coupled compute and memory together, as opposed to compute and memory separate from each other, the dichotomy we have today. And as a result, you enable a lot of high bandwidth. At the time, 8 terabytes per second is high. Today, it's still pretty high, but today we're at a much higher level, of course. And as a result, you get significant performance improvements on 5 different graph processing algorithms at the time. There's more work that has been done after this paper that has improved this to almost 2 orders of magnitude. And the energy reduction is also significant, as you can see over here. So I will not talk more about this, but I think a lot of these systems can be adapted for machine learning and specialized as well. And there are papers on this topic. We have more recently been looking at graph pattern mining, actually by taking advantage of set representations and representing graph problems using sets, and also designing an instruction set architecture that operates based on sets, where the data structure are sets and operations are set union and intersection. You can simplify a lot of things, and you can accelerate graph pattern mining even more than what we have shown in the previous work, but I'm not going to talk about that. Let me quickly talk about the work that I mentioned that we did with Google before I moved to processing using memory. We wanted to understand the bottlenecks in data movement in accelerators using the neural networks that were used at Google, edge neural networks. These are edge devices, edge neural networks at the time. So we analyzed these neural networks, and we found out there's a significant heterogeneity in the characteristics across different models. So you can see that on the y-axis, we have arithmetic intensity. On the x-axis, we have parameter footprint. And there are orders of magnitude difference in terms of these metrics across different models. So layers from large models at the time, LSTMs and transducers are over here. Layers from, let's say, smaller models are over here. So that's one example. So this example kind of motivates that designing a one-size-fits-all accelerator is probably not a good idea, because you need to cater for huge arithmetic intensity as well as extremely small arithmetic intensity and small parameter footprint as well as very high parameter footprint at the same time, and it's very difficult to do so. There's also a variation within each model. These are layers from different CNNs in this particular case, and there's almost 200x plus variation in multiply and accumulated intensity as well as arithmetic intensity across different layers. So what we developed is a heterogeneous accelerator, kind of intuitive after you see those results, as opposed to having a monolithic accelerator, which is not a good fit for everything. We have 3 different types of accelerators in this particular case. One of them is a compute-centric accelerator, and 2 of them are more data-centric accelerators. And we optimize the data flow for different types of or families of layers, and we optimize the memory hierarchy, etc. I will not talk about the details of this, but you need to cluster the families, and you need to design the accelerators such that they can cater to different types of layers. So we have compute-centric and data-centric layers in this case. And if you do that, essentially you can improve energy consumption on average by about 3x. And you can also improve throughput by about 3x. What is not shown here, of course, complexity increases because you need to have a software scheduler that decides which layer needs to execute at which accelerator. But there's a lot more opportunity over here that than we exploited, because we didn't completely exploit the parallelism that is there in the heterogeneous accelerators. You can actually do more than what we did, in my opinion. But one thing that's interesting is now the total area cost of these 3 accelerators that I've shown you is actually smaller than the total area cost of the single monolithic accelerator that you would design that's trying to cater for everything. This may be intuitive, but this comes at the cost of complexity. Okay, so that's that. So what I will not talk about is there's a lot more near memory processing work. I want to go to the next stage that accelerates many different types of applications. We do a lot of work on genomics, as I mentioned, and we're also looking at genomics in storage. I believe as data sizes grow and grow, we need to look more and more into storage. And storage system is actually a system by itself. There's memory, there's storage, there's processors, there's everything in there. Why don't we do actually huge data processing inside the storage system? I will kind of foreshadow, but not talk about. There are a lot more examples actually in this paper that we recently updated, this on archive, and we keep updating it. Now it's almost 100 pages. So if you're interested, you can get an overview of processing in memory. We have two works coming up at ASPLOS that look at large language model acceleration using near memory processing. I don't have time to talk about that, but you can find me, or you can come to ASPLOS and you can see some of these works for yourself. They're also online, so you don't need to come to ASPLOS. Okay. Now let me jump into the other area, which is, I think, more forward-looking, which is much harder to do, but I believe it's very important and interesting to explore because it can be much more fundamentally efficient and it can lead to different algorithms, in my opinion. Okay, so this processing using memory. Basically, what can we do by exploiting the analog operational properties of memory circuitry? You can do this in SRAM, DRAM, flash, etc. Many different technologies. I'm going to focus on DRAM. Clearly, DRAM is the dominant memory technology that we have today. Basically, we can do a lot. That's the good news. We can do bulk bitwise copying and initialization. I'm going to start with that. We can do bulk bitwise AND or not majority nor NAND operations, which is good. And you can build many primitives on top of that. You can do random number generation, physical unclonable functions. And you can do more complex computation using lookup tables by adding a little bit more complexity. You can do most of these at low cost, not all of them. And the key idea is to exploit analog computation capability. And the primitive we're going to look at is really activate multiple rows concurrently, multiple word lines. Well, or in sequence, as we will see with copy. Now, this is very interesting, and there's a lot of theory, circuit simulation, etc. And more recently, we've shown a lot that you can actually do many of these operations in commodity off-the-shelf DRAM chips that are not designed for this purpose. I think this is fascinating to me, so I'm going to get to that hopefully a little bit quickly. Because if you can do this in commodity DRAM chips, maybe people can actually try to abuse the DRAM chips to accelerate their machine learning or whatever their favorite application is. And I would encourage people to do that, even though they may not be perfectly reliable initially. Okay, so you get significant performance energy improvements. Let me start simple by looking at something that I believe we're doing completely wrong in our existing systems, meaning copy and initialization of large amounts of data. Google, in their 2015 paper that I mentioned earlier, showed that about approximately 5% of the cycles in their data centers spent on just these two function calls, memmove and memcopy. And clearly, there are many cases where you actually initialize or copy large amounts of data. So how are we doing it today? Because we're processor-centric, everything has to go through the processor, right? Essentially, you move the data all from the memory to the processor to do a page copy, for example. But why don't we do it in the memory? That's the key idea, basically, of the row clone work. And again, maybe showing this picture to a 10-year-old could help. You can ask the 10-year-old, and they will hopefully give you an honest answer. Am I doing the right thing by doing the copy this way? Maybe they'll tell you, why don't you just do it in memory? Okay, maybe we should be designing our systems as 10 years old. It's good to think about it. Okay, so if you can do it in memory, you don't need to go through the processor. You don't need to use the bus. So there are a lot of benefits over here. So you can reduce the latency by more than 10x. You can reduce the energy by more than 70x. In the fastest case. So I'm going to give you the fastest case. The source and destination pages are magically, hopefully by the operating system, mapped to the same DRAM subarray. And you first activate the source row, which brings the data into the row buffer, sense amplifiers. Now data is strong in the sense amplifiers. And then you activate the destination row, which implicitly deactivates the source row and connects the data that you buffered in the row buffer into the destination row. So by doing two consecutive activates, you can actually copy the data very quickly inside a subarray. It requires system support to map the data, of course, but I'm going to actually talk about that system support later on. This is negligible hardware cost. And theory shows that you can improve the latency of a 4 kilobyte page copy by about more than 10x and DRAM energy by more than 70x. So that's theory. I'm going to show you that you can actually do this in real DRAM chips almost perfectly in existing systems by violating the timing parameters. Okay, so that was copying and initialization, cheating. This is computation. Let's talk about computation. It's a little bit harder, but we have 3 rows now, A, B, C. I'm going to show you only 1 bit in each row as opposed to 4 kilobyte or 8 kilobyte, whatever your row granularity is. I'm showing you the bit line, I'm showing you the sense amplifier. I'm going to show you showing you the other side of the sense amplifier, which is a cross-coupled inverter, as you can see. Now, if you concurrently activate these 3 rows, you connect the capacitors to the bit line. And if at least 2 of these capacitors are charged, you get the charge state at the end. If at least 2 of those are discharged, you get the discharge state at the end. And this is a bitwise majority function. So yeah, basically, theory suggests that you have a bitwise majority function if you activate 3 rows concurrent. Bitwise majority is beautiful because you can take C and set it to 1, and you get the OR of A and B. You can take C to set it to 1, set it to 0, and you get the AND of A and B. Now we have bitwise majority, bitwise OR, bitwise AND. You may say this is not functionally complete, and you're right. To be functionally complete, you need an inversion, which is not. And that's a bit harder to get, but it's there. If you enable, for example, row C, the complement is sensed over here. So if you actually pull it back with some additional hardware cost, you have the NOT also. Now, this is a substrate that's functionally complete now. It's a bulk bitwise substrate, so it's really wide. And you can map things to it. For example, we map databases to this substrate, this all in simulation. And we see significant performance improvements by accelerating various type of queries, especially column scans. Again, I'm going through this relatively quickly, but there are many applications that you can map. If this substrate exists, I believe there are a lot of software people who will use their ingenuity to actually map it. But there are already some things that are operating at bulk bitwise level, like web search is designed that way, DNA sequence mapping, encryption, set operations. And we've shown some of these in our papers. Okay, so that was mbit. Now let's talk about how to make it programmable before we move to real DRAM chips. So this is not an easily programmable substrate, but I believe it's very powerful because it's functionally complete. And if you can completely rethink your algorithm, maybe you can take advantage of it in a nice way. But there are some downsides because not everyone can do that. But the substrate is actually a lot more capable than it looks. And we wanted to take advantage of the substrate, and we want to make it more programmable. So user can actually design any operation. It could be a convolution. It could be a matrix vector multiplication or gem, etc. As long as you can express it using AND or NOT logic, we can map it to convert it to majority and NOT logic. This is a majority inverter graph, basically. We can minimize that majority inverter graph using electronic design automation tools that are beautifully developed for superconducting logic and quantum computing, for example. And then we can map that to a sequence of DRAM commands, essentially express that operation as a microprogram. And that microprogram gets stored in the memory controller. And when the program executes that instruction, this needs to be added by a compiler or the programmer, then this microcontroller gets invoked and it basically executes the microprogram. And that's the idea. This way you can actually take advantage of the substrate for any operation. And we've shown different operations, different workloads, etc. This works very nicely for especially low bit width neural networks, for example, but many other things. And we see significant throughput, energy, and application performance improvements compared to both CPUs and GPUs. Okay, that was some DRAM. Let me talk about the state of the art. This was presented at HPCA last year by my PhD student, Geraldo, who's graduating soon and who's looking for positions. If you're interested in hiring, he would be a great person to hire. But basically, one of the issues with this substrate, it's bulk bitwise, meaning it's very wide. That makes it less programmable. It's great for things that are very high SIMD widths, but most of the things in the world are not designed to handle 8 kilobytes or 4 kilobytes of SIMD. A lot of things are designed to handle 512 bits, SIMD instructions of modern ISAs, for example. But DRAM is unfortunately much wider. So in this work, we basically say that we don't want that wide operations all the time. We want to enable the capability such that we can enable narrower with operations like within a match, for example. In DRAM, a match is about 512 bits. So it's nice. If you can independently access these mats, you can really enable, you basically don't do operations on mats where you don't have data in. That's the idea over here. So we need DRAM to be able to do that. This requires changes to the DRAM architecture. But many people have proposed fine-grained DRAM for energy efficiency reasons also. So this is, I think, a good thing to do going into the future. So we segment the word line such that we can access individual DRAM mats. This way, actually, we have a paper that was presented by Ataberk recently, sector DRAM, that does this in an efficient way that I'm not going to talk about. This improves SIMD utilization because you only use the mats that are actually needed. And this enables a multiple instruction, multiple data model because in some other mats, you can execute something else from the same program or some other program. So now you can actually improve your utilization and efficiency. For some things you need, for reduction operations, for example, you need some low-cost interconnects. That's really important. This is near memory processing now. It's not using memory processing, but we need near memory processing and using memory processing together. And most importantly, perhaps, is eases programmability. Now, you could target a traditional compiler to actually do operations over here at the width of the SIMD width that you have. And that's what essentially Geraldo did. He modified the LLVM passes such that it can be targeted to the mats of a DRAM. And this way, we transparently compile code into this MIMDRAM substrate. I'm not going to go through this in detail. You do code identification, code scheduling, and data mapping, and code generation. All of this is automated. It's on our GitHub that I will mention later on. And if you do all of this, you actually get significant performance and efficiency improvements on real workloads that we tested over here. And one of the benefits over here is you can see the numbers are large, and they're large because the hardware is really utilized. So if you look at a GPU, there's a lot of hardware that is not used for computation, as I mentioned earlier, right? But here, you're really using all of the DRAM substrate for computation. Every single cell is operating on things, unless you don't have enough parallelism, of course. Okay, so now let me quickly switch to the last part that I want to talk about. You can say, okay, what are you smoking? This is interesting, but maybe this is 10 years, 20 years down the road. Who knows? I don't know. I hope to. I think row clone should have happened already. But there are reasons it has not happened, and I'm happy to talk about that. But so we actually also investigate what we can do with existing DRAM chips. Can we actually see these functions in real DRAM chips? And the answer is yes, basically. So Ataberk developed this infrastructure, PyDRAM, which essentially violates the DRAM timing parameters to mimic row clone. So if you violate the activate timing parameter in DRAM, you can copy the data in existing DRAM chips from one row to another row in the same subarray. This is building on the compute DRAM work that was done in Princeton. So meaning that existing DRAM chips, even though they're not advertised to do this officially, by violating timing parameters, you can do copy and initialization. And this is an end-to-end substrate where we have an FPGA. In this FPGA, we have a RISC-V processor, a WIMP1. And this, whenever you get a, let's say, copy operation or a random number generation operation, you violate the timing parameters in DRAM and you do the copy inside the DRAM chips. And Ataberk showed that with micro benchmarks, you get significant performance. These are real results, significant performance improvements. The reason the numbers are very large is because that RISC-V processor is very wimpy, 50 megahertz, no tolerance for things. So you will get lower improvements, but you will get improvements. Okay, so that's one example. More recently, we've also shown in HPCA 2024 in Ismail's work that you can do some of these operations that we didn't think we could do, like not inversion operation, NAND and NOR operation in real DRAM chips. Let me summarize very quickly. This is actually a combination of two works. One can copy one row into up to 31 other rows with almost perfect success rate, almost perfect reliability, 99.98%. I'm going to show you that very quickly. But this is basically by violating the timing parameters, you can open many rows concurrently in existing DRAM, and you can copy one row to another row in succession. You can perform the NOT operation with many output operands, and you can perform 16 input AND, NAND, OR, and NOR operations. So you're functionally complete in existing DRAM chips. Maybe not completely reliable, but that's a problem to solve maybe. So this is basically the idea of multi-row copy as opposed to single row copy. In row clone, we copied one row to another. Here, we simultaneously activate many rows so that we can copy the content of one row to many other rows. If you can concurrently activate many rows, you can actually do that. I will not go into the details. So NOT operation, how do you do NOT? I've already mentioned this actually, but in real DRAM chips, you could do this. So these are two different subarrays, subarray 1, subarray 2 over here. They're connected via the same sense amplifier. If you activate the source row, you go through a NOT gate. Basically, if you activate the source row, the complement of the data is on the other side of the sense amplifier. And then if you activate the destination row at this time, you get the complement on the other side. It's in the other subarray, but you get the inversion. There's one disadvantage in existing DRAM. Subarrays don't have enough connectivity. We had done some work on that I'm not going to talk about. But if you change the architecture and improve the connectivity across subarrays, you can do a lot more computation, in my opinion. Okay, how do you do NAND, NOR, and NOR? Basically, you can generalize this. The idea is you have this subarray over here and this subarray, similarly to earlier, but now I'm showing you two cells, A, B, and XY. If you can concurrently activate all those four rows, what the sense amplifier does is it compares the voltage of A and B, average voltage up there, to the average voltage at the bottom, X and Y. And whichever one's greater wins, essentially. You get 1 over there and you get 0 on the other side. Now, if you're able to set your voltages in an appropriate way, for example, in this particular case, you set a reference subarray. This is VDD over 2, and this is X and Y. You can convince yourself that in the compute subarray, you get an AND of X and Y. In the reference subarray, you get the NAND of X and Y. And you can imagine OR and NOR also by setting these reference voltages different. You are able to set the reference voltages this way in existing DRAM chips with some procedure. I'm not going to talk about that. But this is doable in existing DRAM chips, which is fascinating to me. Okay, so basically, there's more in the paper. Now, we actually tested many DRAM chips from multiple manufacturers. This is the success rate of multi-row copying one row to many other destination row, and average is 99.98%, which is not bad. We want 100%, but it may take some time. Okay, I'm not going to talk about everything. These are the success rates of AND, NAND, OR, and NOR operations. Here, your mileage may vary, but on average, we see about 94% success rate when you actually have 16 input operands, for example. And there are some interesting issues over here that we're examining right now. But 94% is a not bad number to begin with, given that these DRAM chips are not designed for this purpose. That's the key, I think. They're designed for only accessing data and nothing else like this. We're abusing DRAM, basically. Okay, there's more in these papers that I'm not going to talk about. Okay, and they're multi-row copies here. So the key question is, what else can we do using commodity memories? Can we improve them such that these operations that we are right now abusing become the norm, maybe 5 years, 10 years, 20 years down the road? I don't know how long it'll take. So you can do true random number generation. I don't have time to talk about that in more detail, probably. But I'd be happy to talk about that if people are interested. We have some recent results on this also. You can do physical unclonable functions. And if you want to do more complicated operations, then you need to do lookup table-based execution, in my opinion. This may add some more complexity, but I think there's more to investigate in lookup table-based execution in memory. You can do all of these operations in Flash, and we've shown in this paper that you can do these reliably in Flash, because in Flash memory, you have a controller that can change the voltages of cells such that you don't get reliability issues. So you can do AND and OR operations with 100% reliability in real Flash chips that we've tested over here that I'm not going to talk about. So other memory technologies, in my opinion, are a little bit easier because either they're more reliable or they have controllers that are already quite powerful to make them more reliable. Okay, so I've covered the two different directions. There's more in this paper, as I mentioned. One thing I should talk about is adoption, because you can design any kind of hardware and imagine any kind of hardware. And if no one uses it, it'll be a beautiful piece of hardware that sits somewhere. And I think we've seen things like this in the past. It's not no one, but over time, people may prefer hardware that are easier to use. So I think we need to solve adoption issues in this sort of memory-centric research, which means that we need to focus a lot on application and software. We need to figure out which applications benefit. And there's a lot of work in this area, but there needs to be more work. We need to talk about programming. And I think we need to support programming to be easier. We have some works in this area that raise the abstraction level to the higher level framework, so that you can actually program these processing in memory systems with higher abstraction levels, or have the compiler compile from existing code bases so that the programmer does minimal things. But there's more to do in that area. We need to talk about enabled system and security support, and there's a lot here. Coherence, synchronization, virtual memory, which is the biggest headache, in my opinion, in existing systems, isolation, communication interfaces. Runtime and compilation systems need to be rethought for this sort of execution. Like data mapping is a big issue, for example, especially when you have heterogeneous systems where you're doing processing in memory as well as processing in the processor, which should be happening, I think. We're not suggesting we will eliminate processing in the processor accelerators. They will all be there. Access and sharing control, isolation, etc. And we need to also keep developing infrastructures to assess benefits and feasibility in a reliable manner. And I think there's more research to be done. It's quite exciting. But these adoption issues need to be thought about. I believe the biggest adoption issue is the mindset and how industry has evolved. We have a huge dichotomy between processing and memory today. Sometimes, even though you see these functions in memory, even memory vendors don't want to move anything, right, on the memory side. So this is a mindset issue. Clearly, you can also call it a business issue, etc. But I believe we need to come to a better business model and better mindset so that we can actually solve the bigger challenges that we have, like energy and performance and sustainability. Okay, in the end, I think we need to revisit the entire stack, but maybe we can get there step by step. Small things like small operations, enabling small things, pushing small functions into memory over time can enable these operations better. Okay, let me conclude. I believe we want fundamentally energy efficient architectures. That means they need to be data-centric. We want fundamentally high performance architectures. I believe that also points us to data-centric. And if you replace this high performance with fundamentally secure, I believe that's also data-centric. And maybe fundamentally robust is also data-centric. There's more over there. Sustainable is also data-centric in my opinion, but sustainability also has other stuff. So for this, I think we need to think about architectures that minimize data movement. So I highlighted major recent advances in processing, especially in DRAM. And I've shown you some results, which is a summary of many other results in the field that can lead to orders of magnitude energy and performance improvements. And what is maybe more fascinating is unmodified DRAM chips are already capable of interesting types of computation. I believe memory should be designed as a combined computation and storage substrate, as opposed to the inactive storage substrate that we treat it as today. And for this, design mindset and flow should change. And I think that's probably the hardest part of the problem over time. So I believe the future is bright, but we need to do a lot more hard work going into the future. And maybe this thing can inspire us a little bit more, because there's no clear distinction between memory and processing in this thing, as far as people have understood it so far. Okay, we've been holding PIM tutorials. There was one yesterday, but we have more. If people are interested in contributing, please contact us or go to the website and submit an abstract. This is with ASPLOS, but if you cannot make it at ASPLOS, we have one at ICS and we have one at ISCA. So I'd be happy to engage the community if you're interested in participating. And we've had very nice invited talks from both industry and academia in the past. The open source, everything that I mentioned is open source, actually. And you can find in our GitHub. If you need help, we'd be happy to help. And the papers are also there. I will acknowledge funding from many folks who have been generous to support our research. And most importantly, I'll acknowledge people who did the hard work, my students and my group and my collaborators, of course. And you can find more information about them in this newsletter if you're interested. Thank you, and I'd be happy to take any questions.
One question I had was, so you mentioned that like isn't it also more efficient if I figure out a lot of reuse to bring the data, let's say L2 cache, right?
Mm-hmm.
And if it's in there, because I'm not keep reading that again and again for like get matrix multiplication kind of problem. Is that a more energy efficient?
You can do that on the memory side also.
In the DRAM architecture significantly change, it's a lot more expensive, no?
But in order to bring data into the L2 cache, you need to read the row.
Yep.
Now, but you can do that on the memory side. If you add some of the caching on the memory side, right? If you do near memory processing, for example, yes. So I don't think. So I think you have a very good point. Using memory processing without caching is not suitable for everything. If you have very high levels of reuse, I think you want to cache on the memory side. And we've shown in a lot of the work like Tesseract, for example, or the Google neural networks, doing that caching on the memory side is a lot more efficient.
Yes. So like during the talk, I don't really say so during the talk you mentioned the success rate is like 99.9%, things like that. But we would know that last mile is very expensive.
Yes.
So let's say that we want to take like a PIM to the level where we can have like a similar success rate as loading logic, which is around like 6 and 7 sigma. So can you comment on what it takes to get the level of like let's say like a success rate? And then do you believe that it's possible or if not, like do you think that at the end of the day that can be like a deal breaker because we may end up with like very large like CC logic or other like compensation or differential logic?
Okay, so let me first say that processing near memory doesn't have this problem. If you do processing near memory, meaning you do logic next to memory, like we do today, logic separately, you wouldn't have the reliability issues as much because you can do any kind of error correction, etc. over there, just like we do. The problem happens only with processing using memory, and 99.98% happens in real DRAM chips that are not designed for this purpose. Just to set the stage right. Now, the question is, of course, how do you get to 100% if you want to do this on the memory side? We're investigating multiple things. That's a research problem, in my opinion. You can design the sense amplification circuitry a little bit better. You can design some inherent error correcting code, some more redundancy on the memory side. I believe, yes, I agree. It's not easy to get to 100%, but we got to try.
Okay.
So the similar issues exist in analog computation anywhere, right? In logic as well. in our RAM, memristors, etc. All of those are also have some similar reliability issues. Now, the good thing is, even in a chip that's not designed for this purpose, we're getting 99.98%. So I have hope. Yeah. And I believe more research will hopefully get there. The harder part is really and or not operations. We start with much lower over there. 94% is a better case. But again, I think maybe we need to put our creativity to those areas where we can get that to be much higher. And then even if you don't get to 100%, maybe you come up with some redundancy techniques. In fact, in some of our papers, we have some redundancy techniques, but they're a bit expensive. You can actually still get to very high reliability, hopefully 100%. So there's still research to be done.
The fundamentals of using pen. So it seems that you use pen to reduce the data movement, but then the benefits is increased computation in the memory. So since you're only benefiting computation, it seems that only compute bound applications would get the most benefit. But then you actually have more data movement in memory bound applications. So it seems like there's a paradox there. Is there like a specific set of applications that you think this is more included for?
Well, I think, I mean, you're pushing computation to the memory side, but you're also reducing data movement at the same time, right?
Yeah, but like, isn't it that compute bound applications mostly have data in like L1 or L2? I mean, that's why like compute bound.
That's true. So those applications, if you're really compute bound, if you are utilizing caches, don't move to PIM, right? So I'm not suggesting all applications should move to the memory side. In fact, we have some works where we analyze the bottlenecks in different applications. It's called the DAMU work, data movement bottlenecks in 2021. It's Geraldo's work also. That classifies many applications. He's like looked at many functions, like thousands of functions. And he basically classifies them to 6 different classes of bottlenecks. One of them is compute bound, never move to memory. The other ones are depending on the intensity of the data movement, like efficiency of the cache, etc. You may want to move to the cache. So yes, there's a methodology that we have developed through which you can decide which function should go to memory or not. Of course, this is limited to some type of processing near memory at this point, but we need more methodologies for this purpose also.
Yeah, I think coding applications, that and showing benefit, I think will definitely help.
Yes.
Yeah, I'll take 2 more questions.
Yeah, so as we all know, we've been using volume architecture so far for so many decades. Do you think this area, like the volume computing, will impact the status of the traditional volume architecture, or will just have some improvements on specific applications?
Yeah.
And do you think there's a way to standardize the email computing?
Okay, yeah, we have a lot of questions. Those are different questions. So von Neumann. I think von Neumann is here to stay. Basically, if you do a near memory processing, for example, that's von Neumann, right? You have a processor next to memory. I believe that's fundamentally von Neumann. If you go to like this analog hot bitwise execution model, that's a little bit different. But you could also incorporate it into the von Neumann architecture, right? Like we did with the SIMDRAM, where you can actually have a sequential execution model, stored program computer, etc. All of the von Neumann hallmarks can be there. So I believe for adoption purposes, we should try to integrate as much as possible. But I believe that this sort of analog bitwise parallel computation can also enable different types of architectures. Now, I think you asked the question of interface, a single interface. That's something that needs to be investigated a lot more. So I don't have a good answer, but we need to. So we're at a stage right now, we don't have any standardized interfaces for PIM. But GPUs also start out that way, right? Over time, one company kind of dominated the field because they were able to come up with a nice programming model that everyone actually worked with. But PIM, we're not there yet. Right? PIM is actually at the point of GPUs, perhaps in 1990s or so. The good news is I think we need to experiment. So I think as people manufacture different hardware, we will understand this more. We need to do simulation, but we need more hardware also.
Thank you. Sure. Last question.
So I have a question about using actual DRAMs for computing. So I saw the numbers on this slide, for example, like a maximum of 32 row copies using a single row. So like I imagine that when you were doing research, you would have done it for larger numbers and then chosen 32. So I wonder like what limited you to 232? Was it reliability? So for example, did you start getting wrong results when you increase the number, or were there some other problems that were?
Yeah. I mean, essentially what limits you is how many rows you can, so basically the reason you can open multiple rows in DRAM is the design of the hierarchical row decoder. Now by violating the timing parameters, normally when you don't violate the timing parameter, you open one row, right? You supply an address and you wait, everything stabilizes and you read from that row. By violating the timing parameter, you're really opening multiple rows, and the rows you open is a function of the hierarchical row decoder, where those bits are in the decoder. So basically, in the end, you're fundamentally limited by two things. One is hierarchical row decoder, what does it look like? And the second is how fast you can violate things. So that's what we found. I believe that's not the highest number, but that's the highest number at the time we reported. So there's more to be found in this area also.
Let's get Professor Mutlu and Aaron.
Okay.